I'm Maxim Jenihin, coming from Tallinn University of Technology, Estonia, and I'll tell you about zamiaCAD. So some motivation. I think that most of you shouldn't be motivated, but still engineers need tools that will allow them to quickly understand and navigate through complex and partially unknown design code. Tools that would be scalable enough to cope with very large designs, and today we have heard a number of questions about the size of supported designs. And then these tools, they should be non-invasive, requiring minimal configuration, so we want the learning curve to be not that steep. And from another hand, in the academic world, there is a number of challenges as well. So if you are a university person and you want to implement an experimental environment to prove feasibility of your idea, then probably creating such an environment is a big effort. And such environments, they usually suffer from weak front ends and from limited shareability. By this I mean that if you have an environment, then sometimes you are shy to share it with somebody else because you know it has some dirty patches and it's constantly work in progress, etc. So we have come up with an open initiative called zamiaCAD. It's an open source platform for hardware design and debug. It can be used as a base for academic research environments, and it can be a practical aid at industry. Providing for convenient design entry, efficient design exploration. It has a scalable front end and a free simulator. Provides for debug infrastructure, and as an open source project, it provides a community support. So basically, we want hardware designers to feel like this hopper guy from YouTube when they are dealing with their routine work related to hardware engineering. So here's the agenda for my talk. First, I'll give you an overview of the framework. Then I'll emphasize some automated bug localization and other research activities that we have around this project. I'll give a short 5-minute live demo of the tool, and I'll end up with conclusions. So this slide I call triplicity of zamiaCAD, because zamiaCAD, first of all, a framework for design and analysis of hardware, and it has an elaboration engine, advanced entry and navigation, makes emphasis on scalability, and considers RTL as a primary abstraction level. From the other hand, it's a platform for integration, because you can do integration of your ideas at the code level. The framework itself is integrated into Eclipse, so you can do some integration at the Eclipse level, and it provides you for some scripting functionality, interactions, so you can do it at this level as well. And then it's an open source project licensed with GPL version 3. All the sources are available at SourceForge, and it has more than 200,000 lines of code written in Java. And if you want to try it, you can actually install it as a plugin for your Eclipse environment, or you can download it as a compiled product for your operating system. So here's the flow of the tool. So as a front end, we support primary VHDL, and we have some initial steps for Verilog, but actually it's not in our, let's say, high priority to-dos at the moment. But for VHDL, we can pass it and obtain abstract syntax tree. And then we can go further and elaborate this and get a semantically resolved elaborated model. We call it IG, instantiation graphs. Both of these models, they are held in Zamia database, which is a proprietary custom-designed database providing for persistence and scalability, and it's highly optimized for performance. Once you have this model, you can do further the other back-end tasks like design analysis, synthesis, and simulation. I was mentioning scalability already several times, so here are some experiments that we have done for our paper presented at VLCI SOC this October. So basically we took a number of designs from ITC99, benchmarks from OpenCourse Design Plasma. Then we took a Leon 3 processor from Geisler Research and created a system on chip out of it, and then another system of chip where we have, for instance, instantiated this processor cores a number of times. So here you can see the size of the designs in terms of code. And then we took a number of available commercial tools, state-of-the-art commercial tools, considered by us the best ones. So here we had state-of-the-art commercial synthesis tool, simulator, elaboration engine. Here was one free simulator, and another tool was a commercial VHDL editor, which does not create elaborated models, it just creates some abstract syntax trees. And then here are some results. So you can see that basically all of the tools, they have failed elaborating large systems on chip. Only a commercial editor has managed to do it, but actually it has ended up with an abstract syntax tree for these designs. And then Zamia has managed to do its job. Okay. Once you have this elaborated model, you can do static analysis. By this I mean precise global tracing, for example, of parts of signals. You can trace through generate statements. You can create backward or forward static slices for some signals going through signal assignments. Having this model, you can match overloaded subprograms precisely. You can detect sourceless or simpless signals. You can do advanced signal value annotations, compute expressions on the fly, do type checks, FSM recognition, and declaration search, for example. This framework, as I have mentioned already, has its own simulator. The simulator is not that robust and powerful as the elaboration engine, but still it's enough for a number of designs. And in case if we cannot simulate with our simulator, then we can import VCD files from external simulators and we can interact with them by scripts. Then here we have also a number of nice features. For example, we can back annotate the values of the signals and variables in the code. We have code coverage analysis and we can highlight it. We can force values and we can jump back and forth between code and waveform. So here's a little bit of research. I'll show it in my demo, but actually in one paper that I've been presenting a month ago in Austin, we have proposed an approach for automated localization of design errors. It's based on static slicing plus analysis of dynamic analysis of code coverage metrics such as statements and conditions. And then we do statistical ranking based on diagnostic tests that we have, and we can assign suspiciousness scores to some statements. And then we can also do static cone inspections. And based on these three steps, we can highlight and determine in the design some candidates for bug locations in case if a bug was detected. By this I mean an assertion has been violated or some test has failed. So Zamia will provide you some candidates for such bug locations automatically. And some properties of this analysis, it provides for accurate localization, it supports large industrial designs compared to some competitor solutions which play only with really small toy designs. We support multiple bugs, and actually we were doing experiments executing this approach on original functional test without need to create a dedicated diagnostic test. Here's an example. So we were playing with one commercial processor design called ROPSI. and there was a bug in a longer and complex conditional assignment. And in fact, one of the conditions was misused. So applying the approach in Zamia, we were able to propose 15 bug location candidates altogether, and the statement where the bug actually was, it was ranked 5, so it was on the 4th place with this particular suspiciousness score. And then we can go further and we can do a similar analysis hierarchically for conditions, such a conditional assignment. And then the condition where the bug actually was, it has one of the highest suspiciousness scores, among others. Okay, so some other research directions. So we are thinking about visualizations of designs by means of RTL graphs, and that is what we are doing. Then we have contributors who want to integrate System C and TLM into Zamia, and we have a paper on this topic as well. And actually, already now in Zamia, you can generate from RTL, VHDL, RTL System C, and this approach provides for very readable output with a good correspondence to the original VHDL. And actually, we are targeting automated abstraction of RTL IP cores into TLM. And here also we consider a better interaction with Eclipse eCore meta models. Okay, so now I'll give a live demo of the tool. Here you can see interface of Zamia. So as a graphical user interface, we rely on Eclipse, and this part of the source code, it's around 20,000 of code lines, while the project, the core of Zamia itself, is around 200,000 lines of code. And here, for example, we can use nice features of design entry. So we have templates. We have, so if we fill in some ports, we can immediately see some outline. Then again, we have templates for architecture. And if we start to use entities, and we have auto-completion, if you press Control Space, you fill in the rest. And then in Zamia, there is the only configuration that you need is a file called buildPath.txt. Here you can specify the top level of the design that you would like to elaborate, and once you do it, press Ctrl S, and then you get the structure of your design. So red nodes here denote instances shaded entities, and blue nodes denote actually the existing entities in the design. Okay. So here you can easily jump between inputs, and you can see interfaces in the outline, but then let's make it more interesting. Let's add some more files into the edited design, change top level, and then we save it. The design is elaborated. Now top level is different, and now we can see actually full headers for all the four bits of the header, containing half headers inside. Again, you can see all the interfaces, and also in the outline for different entities. You can jump to all internal signals, jump to them. Then you can navigate to processes if they are in the design, and also you could see the sensitivity list of the processes. So let's go now to another design, which is a bit larger than this header example. Okay. So here I have this Leon 3 system on chip, which contains more than 3,000 cores. So actually 256 entities with 14 cores on AMBA bus. So we can navigate in this structure and jump through the code.
Hello, Maxim. Just to warn you, 3 minutes remaining.
I see that. Okay, okay.
And then we'll have some questions.
Okay, good. So just I'll end up the demonstration. So you can navigate through design. And further, I'll just want to show you a little bit of simulations that you can do in Zamia. It's another design. And you can see how the simulator looks like. Okay, if I don't have much time left, I'll switch to my presentation back. Coming to conclusions, here's a team that is working on zamiaCAD project. The founder and principal developer of the project is Günther Barsch from Germany. Then we have some people from our university, Tallinn University of Technology in Estonia. We have a good support from Dr. Rainer Dorsch, formerly from IBM, and now he's at Bosch. We interact with some projects and other universities. This project became open source in 2010, and by now we have around 3,000 downloads, and last year we got IBM Faculty Award. So it's easy to try the tool, it's easy to addict because it has all these nice features. Yeah, and you will start dancing. And then it's easy to contribute your ideas and share them with community. To probe further, you can write directly to me, or you can check the website. It has also a number of tutorials, videos, and documents about the project, and you can also check the recent publications about Zamia. So that's it from my side. Thank you.
Thank you very much. We have one question in Bristol from Paddy McCarthy of Infineon.
Going back to near the beginning of your presentation, I was wondering what the Verilog support is, how it's coming along, and when will you get things like the elaboration support?
Okay, as I was mentioning, it's not a priority task for us at the moment. So in case if you face some research projects or companies interested in this part in Zamia, so we may focus more on this part, but currently I cannot tell you any exact dates.
Question from Bristol is Julia of ST Microelectronics.
Maxim, hi. Is it possible to know which exactly commercial tools you were comparing Zamia? Thanks.
Okay, so we were using these commercial tools through your practice license, and this license doesn't allow me to name these tools explicitly. But actually, if you will go to and if you will read this particular paper where we did these experiments, then these tools are mentioned among the related work tools that we have analyzed.
You can find out if you try hard enough. What do the numbers actually mean on that table? It wasn't clear what the numbers meant.
Okay, I'll come back to this table. So actually, these numbers, they've elaboration time in seconds. So I had another table showing an amount of memory used by these tools, but I just removed it from this slide because I didn't have enough time to go into details. But actually, yes, it's true. Zamia makes use of hard disks to persist some data there. And then this zamiaCAD database is also very efficient for that kind of tasks. But then other commercial tools, they were actually failing. They were running out of RAM.
Okay, but just to be clear, these are elaboration times in seconds. Yeah. Okay.
Yes.
We're going to switch to the other sites now. Cambridge first. Ryan?
No, sorry, Mike. Nothing from Cambridge again.
Is it just you, Brian? Is there someone with you? To Eindhoven now.
No questions from Eindhoven.
Okay, and finally, Grenoble.
Is a simple issue. What's the advantage of using Java or the disadvantage of using Java in this kind of development?
Okay, so because this tool is implemented in Java, we don't have problems with cross-platform solutions. So this tool is available for all the operating systems. And then, I don't know, I cannot answer you exactly. It was also a question to me. This design decision was made by Günther some years ago, so we have just joined the project.
Okay. So I think that's our last question. There's no online questions. So the last thing is just to say thank you very much to Maxim. Thank you.